For centuries, humanity has approached the universe as a grand encrypted text, a language written in the stars and the empty spaces between them, waiting for us to decode its rules. The first language we managed to read fluently was general relativity. The physicist John Archibald Wheeler translated it best: "Matter tells space how to curve, and space tells matter how to move." In this reading, gravity is an ongoing, reciprocal dialogue between geometry and mass. It operates not as an invisible tether yanking planets through a static void, but as a continuous conversation. The grammar of this dialogue demands absolute smoothness. The mathematics rely entirely on unbroken, sweeping curves that gracefully deform under the weight of a star. This predictable prose describes our macroscopic world with high accuracy. It tracks the exact orbits of planets and models the collision of distant galaxies with precision. But when we zoom in past the cellular level, down to the subatomic realm, that graceful prose vanishes. We encounter a completely different language: quantum mechanics. Here, smoothness is discarded entirely. The microscopic world operates on a jittery, fragmented syntax, where particles refuse to commit to a single state, existing instead in a superposition, a blur of multiple potentials at once. This occurs not because the math is silent or the particles are hiding from us. The problem is exactly the opposite. The quantum equations offer us entirely too many valid answers at the exact same time. We now possess two distinct grammars for reality. General relativity and quantum mechanics are both rigorously tested, and they both work with unwavering precision. Yet they are mutually untranslatable. If you try to force them into a single equation, the mathematics collapses into nonsense and infinities. Because they directly contradict one another, they cannot both represent the final, foundational truth of the universe. To see exactly where this linguistic breakdown occurs, we have to look for places where reality is stretched to its absolute limits, where both theories are forced to operate simultaneously. The ultimate test site is the singularity at the center of a black hole. At this boundary, enormous mass is crushed into a subatomic point. You need general relativity to calculate the mass, and quantum mechanics for the scale. This is where the two theories physically crash into one another. Relativity demands an infinitely smooth, steepening curve, while quantum mechanics dictates a wildly vibrating, uncertain landscape. You simply cannot draw a smooth curve across a jittery grid. At these extreme edges of our universe, the text we have been reading becomes entirely unreadable. The dialogue breaks down completely. Theoretical physicists end their careers working in this exact gap. Their attempts to reconcile the clash operate as the speculative footnotes at the edge of reality. Concepts like string theory and loop quantum gravity share a unified goal: to invent a completely new underlying alphabet, a root language that both heavy stars and subatomic particles can fluently speak. They suggest a resolution to the paradox by redefining the geometry of space itself. They propose that if you zoom in close enough, the perfectly smooth curves of gravity fracture into discrete, vibrating loops, or microscopic quantum chunks. These frameworks are mathematically brilliant, but as of today, they remain speculative and unproven. We lack the technology required to test them. Modern physics hangs in this tension. We are trying to navigate completely off the edges of the mathematical map, relying on two separate compasses that point in different directions. Which brings us back to the peculiar problem of the quantum realm having entirely too many answers. If a system exists as a blur of multiple potentials, how does it ever finally choose a single state? The answer lies in the concept of measurement. To force a particle out of its superposition, an observer has to interact with it. Human measurement operates as an active intervention. You are not turning on a flashlight to reveal an object already sitting quietly in the dark. The act of observation physically forces the system to make a choice. Measurement does not passively reveal reality, it selects it. We are active participants in finalizing the state of the world. This changes our perspective of the cosmos. We are not an audience sitting in the dark, pressing our faces against the glass to watch the universe perform. The physical truth is far more intimate. Human beings are constructed from the exact same vibrating quantum matter and bound by the exact same curved spacetime that we are trying to observe. Because we are made of the universe, our act of observing these cosmic boundaries is the universe looking back at itself. We spend our lives trying to reconcile these two untranslatable grammars, searching for the rules of the text. But we are not standing outside the pages. We are the grammar of the universe itself, finally learning to speak itself aloud.